Okay, so further ado, we begin with the session undertook by HansPeter Buchler. HansPeter Buchler from Stuttgart on topological states of matter with cold gases and big reactions. So welcome.
So thank you very much. First question. The microphone or anything? Yeah. Four microphones. So is that better like that? Yeah. Good. So first I would like to thank the organizers for inviting me to Taiwan. So it's my very first time here in Taiwan and so far my very good experience. So it's a pleasure to tell you a little bit about our research on topological states of matter with cold vapor gases and also with normal atomic gases. So this is a first part which I will talk about is a collaboration with Norman Yao, Michel Luking and Sebastian Huber and the people in my research group, which is David Peter, which actually now has left physics, Nicolas Lang, Sebastian Weber, which are my PhD students, and there are all the rest of my group members which are working on different things. So I would like to tell you two things today. So one is a very simple idea to realize topological band structures with dipolar gases. And I would like to show you that actually dipole interactions gives rise to a very simple method which gives rise to topological bands. And if I, within the 45 minutes, in the second part I would like to tell you about the neat system, about a one-dimensional system which exhibits Majorana edge states, but the special property of this system is that it's it conserves the number of particles and therefore goes way beyond the typical mean field approach for Majorana edge states, and that it is exactly solvable so that we know exactly the ground state, and therefore is interacting fermionic systems where we know that the edge states exhibit Majorana statistics. So let me first start with an introduction about topological band structure. And I call it on purpose topological band structure to distinguish it from all the different nomenclatura which we have, like topological states and topological phases. So what I would like to talk about is a single particle band property which is independent of the statistics of the particle, where the band structure of the single particle is characterized by a topological quantum state, by a topological number. And therefore, this single band structure also gives rise to edge states. Now this we should distinguish from what one calls topological states or topological phases. So if we would have fermions and fill our band structure up to the Fermi energy such that it becomes an insulator, then we would call it a topological insulator. But please keep in mind that as I'm not having fermions and I don't fill the lowest band, I don't really call this a topological phase or a topological state. So here, what I'm talking about is just the prerequisite of having a topological band structure. If we would fill it with fermions, then we will get a topological state. If we have flat bands and strong interactions, then there is the chance that actually to obtain a fractional topological insulator, like with fractional quantum Hall states. So this is the situation for fermions. So once we have topological bands and we have interactions, or we manage to fill it with fermions, we get to topological insulators or fractional topological states. If we would have to like bosons, then there is still the possibility that if there are flat bands and strong interactions, we can achieve a bosonic fractional topological insulator. So in that sense, my talk will be essentially the prerequisite to make topological bands, and the hope is, or I will hope that I can convince you that there are flat bands and strong interactions, and therefore the system is a very promising setup to make bosonic fractional topological insulator. Now how does a topological band structure naturally appear? So the simplest and most famous way is if you have a homogeneous magnetic field in a lattice which gives rise to the Hofstadter butterfly phenomena. That means that the hopping in a lattice acquires a phase depending on the magnetic field, and therefore our band structures which we achieve is characterized by a Chern number. Then it was the famous proposal by Haldane, which actually he now received the Nobel Prize for, that one can also achieve a topological band structure without time reversal breaking. And this is the setup famous Haldane lattice where one has tunneling which complex tunneling amplitudes in the systems, but it's not characterized by a homogeneous magnetic field. And there are a lot of experimental efforts at the moment in cold gases to realize this system. So one is by lattice shaking in Tillmans-Esslinger groups. There are artificial gauge fields by Emanuel Bloch groups and Ian Spielman. There are synthetic dimensions in the group by Falani, which actually all have already seen the appearance of topological band structures. Now here we have to ask us, how do we actually characterize our topological state? And in the most general definitions, which I will use in the following, because I will also allow disorder in the system, is the statement that if I have a lattice system and apply periodic boundary conditions, I can add a twist to my periodic boundary conditions, which is a phase twist along the x directions and a phase twist along the y direction. And then I can calculate the change of the ground state wave function as a function of this twist in the boundary conditions. And the imaginary part then describes what is generally known as the Verrier curvature. And so if you integrate it over all the twists in the systems, we get a topological number, which is the Chern number. Now in most situations, you know that the Chern number is much simpler defined if we have a true lattice, and I will tell you such a simple definition later. Just keep in mind that this definition we can also use once we have defects in the lattice and don't have translation symmetry anymore. Now in my talk, I would like to speak about dipolar interactions in a system. And one very important aspect of dipolar interaction is that it intrinsically represents some sort of spin-orbit coupling. Because if you think about dipolar interaction, if you have two dipoles, if they are on top of each other, they attract each other. If they are parallel to each other, they repel each other. But everything depends on the internal state. So if the spin is up, they repel. If the spin is down in these directions, they attract. And it's anisotropic in space. So that means that the spin is the dipole moment, and it couples to the orbital degrees of it couples to the orbital degrees of freedom because it's in anisotropic dipole-dipole interaction. And therefore, a dipole-dipole interactions is a natural phenomena of a spin-orbit coupling, which is well known by the famous Einstein-de Haas effect, or it has been, so this is a reference not for the famous Einstein-de Haas effect, but actually for its realization in cold atomic gases, or which was behind the idea of demagnetization cooling, that one can flip a spin and cool the motion of cold gases, as has been demonstrated by the lab by Tillman Pau, or it was also the reason behind pattern formation in spinocondensates by dense damper current. Now, in my talk, I would like to explore these dipole-dipole interactions to generate the topological band structure. And the setup I'm focusing, so I have particles in a 2D lattice, so on the other side I have a particle, I have an internal spin structure which interacts via the dipole-dipole system. And so systems which you can have in mind are polar molecules. In my talk here, I would like to focus on Rydberg atoms because they have a little bit a nicer property which I would like to convince you. But it can certainly be extended to NV centers, atoms with large magnetic dipole moments, and further systems where I can arrange artificial atoms in a periodic way in a two-dimensional setup. So let's start with the setup. So we have the square lattice for simplicity. We have our Rydberg atoms on each side, and we are interested that on each lattice side, the atom is excited into a high-lying Rydberg state. But the Rydberg state has typically a S-wave function, or at higher excitations has a P-wave function. So the idea is that each of these atoms is in a Rydberg state, which is in an S-wave state, and we are interested in two additional states, which is in the P-wave manifold of our Rydberg manifold. So here is, for example, the n equal 45 S state of the Rydberg manifold, because for rubidium our spin has still a spin degree of freedom. The ground state is twofold degenerate, which corresponds to electron spin up, electron spin down. And the P-wave manifold splits by the normal spin-orbit coupling in a hydrogen atom. Therefore, we have the P3 1/2 manifold. There's also the P5 2 manifold up there, but we are not interested in that one. it's energetically well separated from the state which we are interested in. Now we would like to select out of this manifold these three states here. And we can achieve that by applying static electric and static magnetic field. So what an electric field does to these Rydberg levels, it leaves the lowest states degenerate, but to the P states it essentially makes an anti-smiley. So due to the coupling to the higher states and to the lower states, these states get shifted up in energy. These states can only couple to the higher states and are shifted downwards. So therefore, in a static electric field, we obtain something like this. If we apply a magnetic field, it just tilts everything. So the lowest state is tilted in this direction, the P manifold will tilt in this direction. So combining everything, we get a nice separation that these three states are close by. So we have the ground state, and we have two states which are close by in energy and energetically decoupled from all the other states. And in the following, I will really just focus on these three states and argue that these additional states are energetically far away and are therefore not populated. And this allows me to tell you that as all atoms are initially in the S state, I call this my vacuum state or my ground state, and then excitation into blue I call a minus excitation, and then excitations into the P manifold, the red state, I call a plus excitation. And therefore I can characterize this excitation by boson equation and annihilation operators. So I say that the plus state is generated out of the vacuum by an operator Vi plus, so that creates a red excitation at the lattice side A. So in that sense now we are reduced to bosonic particles, but keep in mind that I don't allow the particles, the true particles are the atoms on the lattice side. The atoms are completely frozen, they don't tunnel, they are just trapped inside the lattice. But the full dynamic comes from all these spin excitations given by the Rydberg excitations. Now we can look how the dipole-dipole interaction acts onto the spin excitations. And we can split in 2D the dipole-dipole interactions into three parts. So there's the D0 part, which is the static dipole-dipole interaction one is used to. So that if two spins point up, they repel each other. If they're on top of each other, they attract each other. As we are in 2D, they are just aligned within the plane, and therefore we get the repulsive with the typical 1/r cubed interaction. But then there's the exchange interaction, which is this term here, which denotes the phenomena that if one Rydberg atom is in a plus state, and the nearby Rydberg atom is in a ground state, I can de-excite these plus excitations to the ground state, and excite this Rydberg state to the plus state. So in that sense, it's an excitation hopping where one Rydberg atom hops down and excites the near neighbors Rydberg atoms into its excitation. I can also think about this process. It's the spontaneous emission of a photon from this Rydberg state and the induced and immediate absorption of a photon by the neighboring Rydberg states. But because the wavelength of this process is in a millimeter up to centimeter range, we are very, very close to the near field. And if you look up, the radiation field in the near field is always dipole-dipole in character, and therefore it has exactly the same shape. So I can think of it as spontaneous emission and absorption of a photon, or we can naively also think just it's really an exchange interaction given by the dipole-dipole interaction. And then is the important part, which is the second term, because I can not only make a transition from plus to down, the same term, the D plus, also allows me to make a transition from the minus state to the vacuum, and then I can excite with D plus from the vacuum to the plus state. So here I have the D plus plus operator, but this operator changed the angular momentum by 1, so it de-excites a minus state to the ground state, and excites the ground state of the neighboring Rydberg state to the plus state. But because it changed the angular momentum by 2, it has to pick up a phase which depends on the spatial orientation of the Rydberg atoms. So I can choose an axis of reference which is along the x directions, and the phase which I pick up is just the phase of this interaxis between the process to the x-axis. And this term is actually the spin-orbit coupling, the anisotropic part in the dipole-dipole interaction. So combining everything, what we end up with a purely hopping Hamiltonian for our excitations in the system. So we have the 1 over r cubed long-range or quasi-long-range hopping in the system. We denote by psi our bosonic annihilation operators for the plus and minus state, psi dagger equation operators. The first term accounts for the diagonal hopping, where we don't change angular momentum. And then we have the off-diagonal, which induces a spin flip in the system and picks up a phase depending on the orientation in the lattice. And yes, and as you see, as I've applied static, electric and magnetic field, I actually have broken time reversal symmetry. And if once time reversal symmetry is broken, the T minus is in general not equal to T plus. And in addition, there is an energy shift appearing, which means the two energy levels are not on the same energy, so we measure them with respect to a zero energy, therefore we have a chemical potential between the plus and the minus states. Now we are in deal to actually study the topological properties of this band structure. So Fourier transforming everything, we get the nice property that, so we have now the K is in the first Brion zone, we get the two-dimensional band structure of the system. And now we are in the other positions to determine the Chern number. So because our Hamiltonian is a 2x2 matrix, we can write it as a unit vector times these three Pauli matrices. And that we can now, so this is the important quantity. So for each point in the Brion zone, we can attribute to it a unit vector. And therefore, the Chern number is then defined by the behavior of this unit vector once we integrate over the first Brion zone. And we can think of it that because this vector is a mapping from the Brion zone, which is a torus, onto the unit sphere, it counts how many times we wrap our torus around our unit sphere. And this is another, or the natural definition of the Chern number. So let us start. Does our system indeed give rise to a Chern number? If one doesn't break time reversal symmetry, so if plus and minus are on the same energy state, then as required we don't open up a gap. We have high symmetry points at the gamma points and at the end points. Now both of these points are actually quadratic band touching point. Although it doesn't look quadratic down here, but this linear part here is an artifact of the slow decay of the dipole-dipole interaction. So, because it decays with 1 over r cubed, with dipole interactions you always must get something linear at low momenta k. And this is this peak here, but otherwise it will be a quadratic band touching point. And therefore, if one stretches the lattice, this quadratic band touching point will split into the other points. However, if we add time reversal symmetry breaking terms, then immediately band gaps open up and the system acquires a finite Chern number. Now this doesn't look very nice yet because the bands are not separated, so one can play around a little bit with the parameters and can very easily achieve a setup where the bands are very well separated and we get two Chern numbers, one Chern number -2 for the lower band and Chern number 2 for the upper band. And if you ask where the Chern number 2 comes from, it's actually the property that we exchange two angular momentum in a hopping part, therefore we have the Chern number 2. So if you would do the same process with van der Waals exchange interactions where we can exchange 4 angular momentum, then the Chern number will automatically result in the Chern number C equal 4. Then one can verify indeed there are edge states in the system, so if one uses it on a strip, there are 4 nice edge states appearing, 2 living on the upper edge and 2 living on the lower edge. And in principle, I was a little bit surprised because we have this long-range hopping with 1 over r cubed. I wasn't expecting that the edge states are still exponentially localized. But it turns out that nevertheless, although the hopping decays with the slow power law, the edge states are very well exponentially localized at the edges. Now the most important question is, if you want to realize it, the natural defect is actually a missing atom at the lattice side. So we know, and I can already see on the talk, so we will hear these very beautiful results by Markus Greiner, where they managed to fill an optical lattice with nearly unit filling over large filling fractions. But nevertheless, one has to ask, how many defects can we tolerate until our topological band structure breaks down? And so the natural defect which we have are missing atoms on our lattice site. And therefore we studied the stability of our topological Chern number with respect to missing atoms. And so here, this is the rho is the fraction of missing atoms. So 0.5 means half of the atoms are missing in the lattice. And it's very so remarkable that the Chern number is extremely stable for under this type of disorder. So even for up to 0.3, so 30% of the atoms missing, we can expect still get a very good Chern number C equal 2. And the dashed line here is just a reference curve. So if we would not have the long-range dipolar interactions, but just nearest neighbor interaction in the system, so cut off the dipolar tail, then the stability would be much weaker. So it's really the slowly decay of the dipolar interactions which enhances the stability to nearly 0.5. And 0.5 would be the critical point if one has just random loading of the optical lattice. Then one can play around, ask the questions, are there also flat bands? So playing around with different lattice structure like the honeycomb lattice immediately shows yes, one can achieve very, very flat bands in the systems, but unfortunately one loses the Chern number C equal 2. So if one applies triangular lattice or honeycomb or even Kaufman lattices, one can achieve flat bands, but naturally the Chern number C equal 2 disappears from the system. So with that would be the first part of my talk. I wanted to point out that dipolar interactions is a very, very neat tool to actually engineer topological band structures. And just to remember, in contrast to all alternative methods which require local addressability or very strong inhomogeneous fields, in this setup we just need static magnetic and static electric field without having to drive or without time dependence and without requiring local addressability or very strong gradients in magnetic fields or electric fields. And that actually tells us that it should be much more robust than all the previous proposals so far. And, but that's still work in progress, does the system indeed give rise to a bosonic fractional Chern insulator? We can expect it because it's rather flat band. It has very strong interactions because all the particles are true hardcore bosonic particles. They still have a remaining dipolar repulsion between them. So we expect that there could be the possibility to realize a fractional bosonic Chern insulator in the system. Now, I would like to switch here and come to a second part of my talk, which are Majorana H balls. And before I would like to start, let me just remind you, how can we understand Majorana H states in this one-dimensional system proposed by famous Hittite Majorana chain. So we have our Hamiltonian, which consists of spinless fermions in a 1D lattice with a superfluid pairing term. So we have the hopping term of all the fermions from one lattice side to the next lattice side, and we have a pairing term, a p-wave pairing term, given by some sort of mean field superfluid, which induces a pairing gap into the into our system. And in addition, we have the chemical potential, which defines the filling of the system with fermions. Now, the easiest way to understand that there are H modes appearing is at this special point where W is equal 1, delta is equal, W is equal delta, and the chemical potential is equal 0. Because then we can very easily see that each lattice side, so the blue and the red dots, should be one lattice side across for one fermion. So each gray square corresponds to one fermion and one lattice side. Now the first step is we can split our fermion into two Majorana fermions, into a blue and into a yellow one. By the following procedure, so we write each Fermi operator as C2i minus 1, which is a Majorana operator, plus I C2i. So we split just mathematically each fermion into two different parts with two new operators C, 2i minus 1, C, 2i. And these operators still satisfy Fermi statistics, but they have the special property that C squared is equal to 1. Now, so far one doesn't gain a lot. We can always split the fermion, but the special property of this at this special point is that the parent term for the ground state requires that we now pair up neighboring Majorana fermions back into a new fermion, which is the fermion which is given by a Buchler transformation. So, we know that we can perform a Buchler transformation of this Hamiltonian. If we perform this Buchler transformation, it corresponds exactly that we pair up two neighboring Majoranas into a new one, but these two Majoranas are not on the same lattice side anymore. And if we perform this procedure, we again get a nice Hamiltonian on this side, but there are two Majoranas left, the green one on the left edge, and one Majorana operator on the right edge. And in this way we can understand that this Hamiltonian gives rise to localized edge states, and the ground state degeneracy is twofold degenerate because these two Majoranas still give rise to one fermionic operator. But this fermion is spread between the two edges, and therefore no local perturbation can split the energy. The energy splitting can give rise to energy splitting between a state where this fermion is unoccupied and a state where this fermion is occupied. Good, and the characteristic property, if you look at the, if you go away from this nice exactly solvable point, then it's still exactly solvable, but we see that the edge states are no longer exactly at one position, but they can decay exponentially from the edge into the system. Now, why should we care about it? So first, it's a state which has a very robust ground state degeneracy, and it has been a lot of proposals to use it for robust quantum memory. Whether this can really work is not part of my talk. There have been ideas that, yes, these edge states are actually non-abelian anyons, and therefore they are one of these exotic particles which give rise to non-abelian braiding statistics, which might be used for topological quantum computation. But my motivation is more that such Majorana states is novel states of matter which we would like to explore, and it's a true toy model for a topological phase. Now what I would like to do in my talk is the following question. In Kitaev's Majorana chain we always have to assume this type of Hamiltonian which already imprints a very strong superconducting pairing into the system. And therefore it breaks particle conservation. It still has a parity conservation, but the particle number in our system is no longer conserved and requires a huge superconductor attached to the system. And I can ask the question, if it starts with a microscopic system of just one wire, can there be Majorana edge states in a particle number conserving setup? And this I would like to demonstrate to you that indeed the best what one can obtain, there is an exactly solvable model which exhibits Majorana-like edge states in a microscopic model of spinless fermions. And this I would like to present you in the following. Let me just shortly tell you there are different approaches to this so far. So one is based on bosonization procedure that where one in principle can also show that bosonization is consistent with Majorana modes in a particle conserving setup. There has been some numerical approaches by Christina Kraus in Innsbruck, and there is an exactly solvable model which influences long-range hopping and long-range interaction. However, here we will just use short-range interactions and a local theory for spinless fermions. So let me start to describe the Hamiltonian. So what we study is a two-leg wire. So we have two wires filled with spinless fermions. And we have three Hamiltonians. We have one Hamiltonian describing the wire A, we have one Hamiltonian describing the wire B, and then we have the interchain interactions HAB. So the interactions between in the upper wire is the same as in the lower wire and can be written in the following simple simple way. So we have an operator AI times 1 plus AI. I will tell you immediately why we write it in such a strange shape to motivate you that you can find the exact solution. And the interchain Hamiltonian has the same shape, that it's an operator BI, 1 plus BI. So we have the interactions between nearest neighbor sides within the wire, and then we have a 4 sides interaction between the two wires. Now I have to tell you how the interaction looks exactly within each wire. So for within the wire, we denote by A, so X is A for the upper wire, B for the lower wire. So we have this operator A which describes nearest neighbor particle tunneling. So therefore, the A times 1 plus A, the first term, the 1, describes just nearest neighbor tunneling in the system. And then you have the A squared term, which, if you expand it, describes some nearest neighbor repulsion, nearest neighbor attraction in the system with a chemical potential 1. Now the special point of this state is the following. Think of it, if there is a particle and it can hop to this side, then there is a state which is the equal weight superposition of the particle being on this side and the particle being on this side. If it is the equal weight, this Hamiltonian gives actually 0. Because the first term tells us, yes, we can hop the system, therefore we gain the energy. But the second term, because it's a projector A squared, exactly pays the same energy again. Therefore, this Hamiltonian is what is called frustration-free. So the lowest energy states which are possible are 0 energy states. And if we find a state with 0 energy, it is actually the ground state. So we just have to look, what are all the states of this Hamiltonian with 0 energy? And it's really the idea that if a particle can hop, we gain energy by the hopping, we pay the same energy by the interaction, and therefore the Hamiltonian gets 0. And therefore it's immediately easy to show, no, not so easy, but straightforward, that the ground state of this system, we have a fixed number of particles n on our wire, and the ground state is just the equal weight superposition to distribute all fermions onto this wire. So that needs a few explanations. So keep in mind that we have fermions, so we need an ordering string. So we order our fermions from the left to the right. And then we can define just the sum, so a state which is a distribution to distribute our n fermions onto the wire, which is represented by here. And then we make the equal weight superposition of all these distributions. Now, why is this an interesting state? And the point is, this is nearly the Kitaev's-Majorana chain ground state which I've shown you before. So if you go back and look at the Kitaev's-Majorana chain, here the difference is that the ground state which I demonstrated you here is the equal weight superposition to distribute an even number of fermions onto a one-dimensional chain. Because we don't have particle conservation, we don't distribute a fixed number, but just the idea is that we distribute an even number. And the second ground state, where we feel the edge state, is where we distribute an odd number of particles. So therefore, what we have achieved here is already something very close to the Kitaev's-Majorana chain, because now we have the equal weight superposition, but now we have the fixed number of particles distributed onto the system. But now it's probably clear how to achieve a nice state, because we have two wires. We now want to allow pairs to hop between the two wires, such that the ground state is the equal weight superposition to distribute total number of n particles between the two wires which are distinguished that one wire has even and the other wire has odd parity. So let us achieve that by the following Hamiltonian. So again we write it as a frustration-free Hamiltonian, such that if we find a 0 energy state, we know that it is the ground state. We write the term as a pair hopping term. So if two particles are on the upper wire, they can hop to the lower wire. Once they do that, we want to be in an equal weight superposition. By this process we gain energy, and therefore the B squared term pays the same energy once this process is possible, and therefore the Hamiltonian becomes 0. That means that all states which are the equal weight superposition to distribute n particles onto the wires is a ground state of our Hamiltonian, and one can easily show that it's actually the unique ground state, up to a degeneracy which I would like to mention next. So let's focus that we have two open chains. Now I told you that we can distribute our particles, that we have the equal weight superposition to distribute our particles onto the wire, but there are two ways to do it. We can either have an even number in the upper chain and an odd number in the lower chain. And this is exactly the two ground state degeneracy which we knew from the Kitaev-Majorana chain. So again, our Hamiltonian has a twofold ground state degeneracy, one characterized by an even number on the upper chain, one characterized by an odd number on the lower chain. So this is the situation how the distribution, the two ground state looks like if you have a total even number of particles. Does need immediate extensions if the total number is odd. And if we close the wire and make periodic boundary conditions, so if you have a closed loop, then there's just one ground state appearing, namely for odd number of particles. Now what is interesting is that the construction doesn't really matter how we distribute our wires, whether they end at some point or we can add more wires to the system. So if we add a hole into our wire, we still get the same construction to get the exact ground state, and then we can start to count the ground state degeneracy by the number of edges which are in the system. So, for example, if I start with this setup, the ground state degeneracy is given by number of edges E divided by 2 minus 1. So in these situations I have 1, 2, 3, 4, 5, 6, 7, 8, 9, or could be odd, even. Yeah. No, I didn't make it even in this situation, so somewhere there must another edge appearing. But you see that whenever we cut it in such a way and we get an edge in the system, we get a new ground state degeneracy by a factor of 2. And that's already a first indication that there are Majorana-like physics appearing, because the ground state degeneracy scales like square root with the number of edges. That's exactly what one expects for Kitae's Majorana chain. The minus 1 is just the restrictions that we have the total particle number conserved, and therefore two states actually disappear by this constraint that the particle number is fixed. Then we can look at the ground state properties, and indeed the system shows exactly what one expects. So we have exponentially decaying edge stages in a system. We have all correlations decay exponentially, so the density-density correlations is just a constant. What is a little bit strange and requires explanation is the superfluid pairing correlations is actually long range. And I will tell you immediately more about that in the future, because the argument is we are in one dimension, and according to Wernher-Wagner's theorem, we shouldn't have true long range order in a superconductor, but I will tell you immediately that is not a contradiction. So we have a true long-range superfluid pairing, and all other correlation functions decay exponentially. And especially we have localized edge modes which exhibit their revival at the other edge. And all these properties can be just calculated by binomial factors. Let me skip the ground state properties so we can analyze whether they, just shortly. So then one can analyze, is the ground state actually robust to perturbation? And indeed, if we separate our edges by a certain distance, there is no local perturbation which can flip the ground state or provides a finite overlap. And surprisingly, not even time reversal symmetry. So, in that sense, the topological order here does not require a symmetry to protect it. But that is a dangerous statement. I will come to that a little bit later. But at this exactly soluble point, the topological order is protected by there is no symmetry required to protect it. Once the two edge states are separated, once they are just on top of each other, like here, then we need, for example, time reversal symmetry breaking to protect the topological order. Now the next question is, what about the excitation spectrum? Is this a gapped phase, or is it a phase with, or is it an ungapped phase? And one can immediately expect, because we have superfluid long-range order, there should be the analog of a Goldstone mode, and the Goldstone mode should give rise to a gapless excitation spectrum. And indeed, one can show that this state here is actually also the exact eigenstate of the Hamiltonian, and it has a quadratic dispersion relation, so we get a quadratic dispersion relation, so the excitation spectrum is ungapped, and therefore we get a Goldstone with a quadratic dispersion relation. Now this indicates, on the other hand, also that our system has vanishing compressibility. So it's exactly at the critical point where the compressibility vanishes, and that we can also understand because for each number of particles we get a ground state with zero energy. Therefore it doesn't cost us energy to add a particle, because once we add a few particles, the state has exactly the same energy and still zero. So we get for every number of particles we get a ground state with zero energy, and therefore the compressibility has to vanish. And because the compressibility vanishes, we get a quadratic Goldstone mode. And therefore this explains also why we get two superfluid long-range order. If you have non-interacting bosons in one dimensions, they can form a perfect Bose-Einstein condensate. At zero temperature, all bosons condense into the K equals 0 mode, because they are non-interacting. Because they are non-interacting, they have a quadratic dispersion relations, and their compressibility vanishes. Another example where we have two long-range order is a Heisenberg ferromagnet in one dimensions. For a Heisenberg ferromagnet, all spins point in the same direction. Therefore, we have trivial true long-range order. The excitations are magnons, which have a quadratic dispersion relations. The system is very close to phase separations, which means that one spins point up, the other spins points down if you go away from the exact Heisenberg point. So we know exactly that, yes, inwardly it is actually allowed to have superfluid long-range order, Alford, and is not in contradiction to Bernoulli-Wagner's theorem. Now, for the last 2 minutes, so what are the indications that the H states behave Majorana-like? So far I've shown you the ground state degeneracy, which is consistent with Majorana physics. It's very closely related to the Kitaev-Majorana wire, which also indicates there should be Majorana physics inside. But to be truly sure, we actually should calculate the braiding statistics. And this is now a setup where one can test the braiding statistics analytically. So each of these systems is a double wire setup. So we don't draw, so each of these red line is connected by a second line, which is the second wire, but we're not so much interested in the second wires, we are mainly interested in these two H states here. And what I would like to show in this figure is, so we start where these H's are also connected. So there are 2 points. We are in a gapless space, but because we are in a finite system, we can go in coupling strengths here below the finite size energy gap, and therefore then just restrict everything into lowest perturbation theory onto the 4 states which are here. So what we are doing is the following. So we start with the setup where we insert this picture up here. So that means these 2 wires are connected with each other, and therefore we have 2 Majorana states one at this edge and one at this edge. Now we want to braid these Majorana states around each other. So what we can achieve is we turn adiabatically this coupling off and turn this coupling on. What it achieves is it moves this Majorana mode to this edge. Then we can adiabatically turn off this and adiabatically turn on this coupling, which moves the next H state to its pivot position. And once we do it twice, you see following this procedure, we've exchanged the 2 H states around each other. Now we can follow how the ground state changes once we've under this procedure. And indeed, once we start that this wire is empty, doesn't include a fermion, and this wire is also in a 0 state, after braiding the two mirrors around each other, we end up with the state which is 1, 1, which is exactly the signature of the Ising non-abelian braiding statistics. And with that, thank you for your attention.
Okay, so we have time for a couple of questions maybe before the coffee break. Yeah.
In your first part of the talk, you had this average churn number against percentage of missing particles.
Yes.
And there's one reference line where you didn't have the spin of the dipole. Okay.
There's one part where you had a reference line where you didn't have the dipolar interaction. You have that one? So what's giving rise to the non-zero churn number? Is it just the hopping?
Again?
That reference line where you said you didn't have the dipolar interactions?
So you have the dipolar interaction, you just take the same system, but you cut off the dipolar interaction at some deep range.
Right. So there is still some amount of it.
Yes, so instead of taking the full 1/r cubed interaction, you just cut it off at a certain range. And we cut it off at the nearest possible point, which is actually square root 2 of the lattice side. So that means that we still can hop from here to here. These two can also have an interaction, but we don't include an interaction between this one and this one anymore. So it's the same system where we cut off the dipolar interactions at a certain range.
But if it's exactly 0, then I expect a 0 churn number, at the 0% of missing particles, right?
So how can you get an average churn number? So this is the disorder average. So in each realizations, you either get 2 or 0. But for some disorder realizations, you have chosen a disorder which gives 0, and some disorder realizations gives 2. And therefore you average over many disorder realizations, and therefore you get a smooth curve. So that tells you that down here, most of the realization in the finite size systems have 0 churn number. Up here, most of them have churn number 2. In a thermodynamic limit, we have self-averaging, and therefore this should become a sharp transition, but we cannot simulate the large system size. So from black, red to blue is increasing the system size, and you see that the transition becomes sharper, and in a thermodynamic limit, we should just get either 2 or 0 at the sharp transition point.
Right. Yeah,
So why does the long range part sort of stabilize the churn number? So you cut off, then it becomes less stable, right?
Yes, so it's...
is there an easy way to understand this phenomena?
Yes and no. So it's very counterintuitive because for magnetic fields it would be otherwise. So because if your magnetic field is just a flux field circle, then typically you would expect if you make a loop which is very large, the flux just averages out. Here the special property is that it just matters on the angle which you tunnel. The phase which you pick up is just given by the angle and not by the distance. So if you just have nearest neighbor, then you see still some properties of your lattice. Once you go next nearest neighbor, next nearest neighbor, the system looks much more like a homogeneous system. And actually you can make a transition. So if you cut off, so there are some ideas that you cut off the short range hopping and just have long range hopping, then you always get churn number C equal 2, and you can get rid of the disorder at all. So then you can just have a gas of frozen atoms. As long as the range, you don't have some short range hoppings, just a range of hopping larger than an interparticle distance, you will immediately get churn number C equal 2, and the long range again stabilizes it, because it's just the angle and not the area which encloses which determines the flux.
Okay, I think it's time to move on. We have a coffee break now. Let's thank HansPeter for the center.
Should sound next outside. So yeah.